Hello. In previous video I show you how we can use the tooled operational semantics of Lingua Franca to have omniscient debugging and also to check some properties by defining assertion in the model like this one. And in this video I will show you how we can use the very same environment for model checking. So what we will do is that actually we will run the very same system. So use a run configuration and duplicate the configurations, but this time I will ask for exhaustive simulations. So I rename this file and I remove the engine add-on because I don't need them, and I will check this box asking for exhaustive simulation here. Okay, so let's run it. So the system actually goes through the different state of the model, and I will come back as soon as it is computed. Alright, so the state space have been computed, so it is now in our folder here. We got two representations, the .classical format and this format, which is suitable for model checking in the CADP tool, which is a model checker from Grenoble, France. Okay, so let's see what we can do with that. First, we can have a quick look at this dot file. So let's open it. Okay, so this is actually our state space. I will not go into detail. We can see interleavings and so on, but something which is interesting is that we can look for the time jump here. So I will look for some edge label attributes that includes time jump, and here we are. And here we can see the time jump. And what we can see is that the interleavings occur in between the time jumps. So the time jumps act as a barrier of synchronizations between the different causalities of the systems. Alright, so this is just visualization to understand, but more interestingly, what we can do with that is that we can model check it. So let's, so this is the state space. Let's go in the model checking folder. Here I actually define two properties. So I will not detail them, okay. These properties are defined in the model checking language. So the model checking language is defined here if you want to have a look. It's classical temporal logic, but extended with the possibility to make evaluations on label, to use regular expression and so on. So I got two different properties here. The first one says that the different reaction image obstacle detection 2 and LiDAR obstacle detection 2 always happens in the same logical step. Okay, so in between two time jumps. And so this one should be actually fulfilled, and this one says that the very same reactions are always synchronous, which is actually wrong because it can be interleaved in the same logical step. Okay, so let's see what we can verify with that. So first, I just copy the previously generated state space in the current folder here, and I has to evaluate the properties on this state space, and the first property I will use is always in same logical step. So it's auto where always in same logical step. I just run the model checker and it gives me true. It gives me also a diagnostic in the form of a graph, which is a dot graph that I provide you here as a PDF. And you can see that you can either have one ordering, the other ordering, or both of them synchronously. Okay, we will not get into detail into this. This is not very interesting. What is more interesting is when the properties is actually not verified. So I want to check if they are always synchronous. So this time it's false. It gives me also a diagnosis in the form of a dot file, and if I look at the file, it may be boring to understand why it does not work. Okay, so this is where this is interesting. We can go back in our Lingua Franca environment here, and if I just refresh the folder, I will have the diagnostic here. What I will do now is that I want to inject this diagnostic into the execution so that I can play this diagnostic directly in my environment. Okay, so let's do it. So I just select this diagnostic in the dot file, and I also select the original time models that were generated before. I'm asked to generate a new specific constraints that will actually force the execution to follow the one from the trace in the diagnostic. Okay, so this is done here. I've got this new spec, and just like with the assertion, I will create a new debug configurations, which will clone the debug one. Okay, debug counterexample, and I will keep the different add-ons here, and in the advanced tab I will pick now this newly generated extended CCSL, which adds a counterexample to the original time model. Okay, so I'm just pick it, I launch the debug, and I'm in the very same environment and I show you. But this time I've got a single solution for each step because it's constrained by the counterexample. So let's follow this counterexample. So we have the same feedback in the console outputs, in the animation of the models, and we can understand the counterexample which was actually provided to us by the model checking tools. Okay, we just replay this counterexample, but in the original environment. Okay, and here we can see that we can do this specific order, and at this step, actually, okay, not exactly at this step. Yeah, at this step, I can start by executing this LiDAR action before to execute other actions, and later on this other reaction here. Okay, so it shows me the actual counterexample directly in the original environment. I can try to figure out why it happens and either modify my model or try to understand if the property I wanted to check does actually make sense on my system. And I can play it. What you can see is that once again in this trace you always got a single possibility constrained by the counterexample.